All right, welcome back to Inorganic TUTOR'S Institute. In today's lecture, we are basically going to look at how we can handle this particular problem on the board. So, first of all, this problem has already been solved, but we want to use another alternative way to handle this particular problem. Okay, but before I begin, let me say a very big shout out to all vector algebra and differential equation students. Big ups to you all. Thank you very much for always following me up. All right, now this is the problem. All right, by differentiating this particular function, okay, we want to verify that this function is an integrating factor to this differential equation. Okay, hence, we want to solve this particular function, right? This is the differential equation that we want to solve. Okay, so what does this question require of us? All that this question wants us to do is to verify this integrating factor, and if it works, then we use it to solve this particular differential equation. But the question didn't specify that we should use the integrating factor to solve the differential equation. So in my first video, I used the substitution approach to handle this particular differential equation. But in here, we are going to use the integrating factor to multiply this differential equation, then we will solve it. Because this is an exact differential equation, but at this moment, this is in the form of the exact differential equation, but at this moment, it is not exact. But once we multiply through by the integrating factor, it becomes exact. Then we can solve it using the exact approach. All right, so let's first verify this function. If it is an integrating factor, then we can use it to multiply through this differential equation and then solve it, right? Okay, so first of all, let's verify. Okay, so let's begin with the process. All right, so we want to verify that this function is an integrating factor to this particular differential equation. All right, so let's say that mu of x and y, we are letting this function represent mu of x and y, which is the integrating factor, right? So 1 over xy into f of xy minus big F of xy, all in big brackets, right? So this here, right, we can see that this particular function itself is a product of only x and y, right? It's a product of only x and y. So we can use substitution, right? We can use substitution, which is by letting u represent what? The xy. Okay, so let's begin with that. So first of all, we have let this function represent what? The integrating factor, of which we are going to verify if indeed it is the integrating factor. So we are going to start the process. So by differentiating this integration function, right? So we are going to differentiate this, of which we are going to do total differential, right? So from here, we are going to differentiate this. So let's say, first of all, let's u equals x, y, okay? So that we will avoid xy in the process throughout, but at the end, we'll go and substitute, right? So if we say that u should be equal to xy, then it means that when we apply the differentiation on both sides, then we say that the u should be equal to, you differentiate x, then you maintain y. So we have y, the x plus maintain x, then you differentiate y, right? So this is what we have. Now, we divide true by u, here true by u, right? So we're going to have here, don't forget that our u is xy, so we have xy divided by sy, and that is equal to x dy divided by xy plus y dx divided by xy, right? So we go here, and we say that d of xy divided by xy is equal to, this cancels this, and then we have 1 over y dy plus this cancels this, so we have 1 over x dx, right? So now this here, we have been able to differentiate that to have this. So let's note that down. Okay, now let's come to the natural log function, right? So we have ln into x over y, right? So we know that this ln function can be expressed as ln into x minus ln into what? Y, right? So differentiating these ln functions, we know that when you apply the differentiation on it, we are going to have ln into x minus ln into what? Y, right? So you know how to differentiate ln function, right? You take 1 over the function inside the ln, then you differentiate the function inside the ln. So we are going to say that differential of ln x minus differential of what? Ln y, right? And here, when you differentiate ln x, it means that you are going to take 1 over the inside function. So we have 1 over x times, we differentiate the x, so we have the x, right? Minus 1 over y, of which we have here, times differential of y. Okay, so that is how we differentiate a function inside the ln, right? So finally, we have 1 over x dx minus what? 1 over y dy. And that is the differential of ln into x over what? Y. So in here, we know that this is that. So we have been able to differentiate this, and we have been able to differentiate this respectively. So this is there, and this is also there. So now we are coming to do what? Total differential. So we come and substitute this here. We substitute that here. Okay, so let me clean up this. So we're going to have our total differential represented as this to be equal to differential of what? Full differential of what? This of f of xy. Don't forget that our xy, earlier on we said that it should be what? U, right? From here. So we're going to say that this part should be u, right? So let me try to put that down here for you. So we're going to have, since f of xy is u, then it means that f of x y will be what? F of u. Then big f of xy will also be big f of what? U, right? So in here, we're going to have small f of u plus big f of what? U, divided by small f of u minus big f of what? U, times, in here, we have what? This here, we know that it's now this. So we're going to have 1 over y dy plus 1 over x dx, right? Then we go on to add the ln function, right? So plus this 1 over x dx minus 1 over y dy, right? And that is equal to what? The c, a constant. So that is basically 0, right? So this is equal to 0. Okay. Now let's calm down. Let's calm down. So from here, we know that applying the total differential, we're going to have our total differential to be equal to f of u plus small f of u, big F of u divided by f of u minus big F of u, right? Times 1 over y dy plus 1 over x dx plus 1 over x dx minus 1 over y dy. Okay, so this is what we have. Now we know that this is basically going to give us this. This will carry this, so let's try to write that. So we're going to have f of u plus big F of u divided by small f of u minus big F of u times this and this, right? So we're going to have 1 over x plus 1 over x all the x plus small f of u plus big F of u divided by small f of u minus big F of u times 1 over y minus 1 over y all dy, right? So we're going to see that still this is our total differential, right? So we go up here, then we see that our total differential is equal to this here. You can say that we have f of u plus big F of u divided by small f of u minus big F of u times 1 over x plus 1 over x all the x plus small f of u plus big F of u divided by small f of u minus big F of u times 1 over y minus 1 over y all dy, right? So we can see that this right here and this right here, this we can separate, we can factorize 1 over x out, right? So in there, when we do that, we're going to have our total differential to be equal to 1 over x into f of u plus big F of u divided by small f of u minus big F of u times 1 over x plus 1, right? All the x, right? Plus small f of u plus big F of u divided by small f of u minus big F of u times 1 over y minus 1, right? So all this times dy. Okay, So this is what we have so far. So we can see from here that we can still do some calculations, right? So from here, we know that this here this is going to be plus 1 here, then minus 1 here, right? Okay, so that when we expand back, we're going to have our, when we expand this, we're going to have this. When we expand this, we're going to have that, right? So in here, we know that this is our LCM for this, right? So when we do that, we're going to have our total differential to be equal to 1 on x into f of u plus big F of u plus this, right? F of u minus big F of u divided by small f of u minus big F of u, right? So this, all the x plus 1 over y into small f of u plus big F of u minus small f of u plus big F of u, all divided by small f of u minus big F of u, right? So all dy, right? So this is what we have so far. So let's come up here. So we come up here, we're going to have our total differential to be equal to, 1 over x multiplied by this big F of x, big F of what? U will take this big F of u. So we're going to have F of u plus small f of u, right? Divided by small f of u minus big F of u, right? Or the x, right? Plus 1 over y multiplied by, now this small f of u will take this small f of u. So we're going to have big F of u plus big F of u divided by small f of u minus big F of u, right? All multiplied by the y. Okay, so this is where we've gotten to so far. So from here, let's simplify this. So we're going to have our total differential to be equal to 1 over x multiplied by, this is small f of u plus small f of u. So we're going to have 2 times f of u, small f of u, right? Divided by f of u minus big F of u, right? The x plus big F of u plus big F of u. We're going to have 2 big F of u, right? All divided by small f of u minus big F of u, right? Or dy. Okay, so this is what we have so far. But don't forget that this is common here. 2 is common here and 2 is common here. So we can divide through by 2 and then this 2 will go off, right? So we come up here, we say that our total differential equals 1 over x times f of u divided by small f of u minus big F of u, or the x plus, here too we multiply that and we're going to have divided by small f of u minus big F of u dy, right? So this is what we have so far. Because 2 is common to all, we divided through by 2 and the 2 is off. So this is what we have so far. So now let's try to move up here. So that is the verification process, right? So we're going to say that our total differential equals 1 over x small f of u divided by x times small f of u minus big F of u dx plus big F of u divided by y times small f of u minus big F of u, right? Or dy, right? So this is what we have. Now we can see that this and this are the common denominators. So that will be our LCM. So our LCM is going to be x times y multiplied by small f of u minus big F of u, right? So you're going to multiply this throughout this each of the term, right? So we're going to do that. We're going to have our total differential to be equal to what? When you do that, it means that this will multiply here, so this will go off, then x2 will go off, so we're going to have only y. So we have y times f small f of u dx plus, when this multiply this section 2, this will go off and the y2 will go off, right? So we're going to have big F of u times x dy, right? So we have our total differential to be equal to small f of u times y dx plus big F of u times x dy, right? And this is what we have, of which we have been able to prove that that integrating factor is indeed an integrating factor to the differential equation. So this here, we know that the total differential is equal to what? 0. So in here, this is equal to 0. So we're going to say that small f of u times y dx plus big F of u times x dy is equal to 0, right? So this proves that the differential equation, this differential equation that we have gotten, proves that that integrating factor is indeed an integrating factor. So let's conclude that here. Let's conclude that here. So this confirms that of mu of x and y equals what? 1 over xy into small f of xy minus big F of xy is indeed an integrating factor to the differential equation. Okay, but don't forget that we said u should be equal to what? Xy. So let's try to substitute that so that we have small f of xy times y dx plus big F of xy times x dy equals what? 0. So this is what is confirming that this is indeed an integrating factor. So we are done with the verification. Now let's solve the differential equation that we were given. So let's continue from there. So that is the verification process, okay? It's not difficult at all. It's not difficult. So hence we want to solve. Now this is the differential equation that we want to solve. And we want to use the integrating factor approach to solve this problem because this is not exact. But once we multiply through by the integrating factor, this becomes exact automatically, right? So from here, we say that f of x y should be equal to x squared y squared plus xy plus 1, right? And then our big F of xy should be equal to s squared y squared minus xy plus 1, right? So this becomes our small f of xy and this becomes our big F of xy. So we are going to use this to simplify the integrating factor, okay? So now let's say that small f of xy minus big F of xy is equal to this minus this. So we're going to have s squared y squared plus xy plus 1 minus s squared y squared minus xy plus 1 will be equal to s squared y squared plus xy plus 1 minus s squared y squared plus xy minus 1, right? So this takes off this and this also takes off this. So we're going to have 2xy. Okay, so this is what we have so far. But we know that our integrating factor, which is mu of x and y, is equal to what? 1 over xy multiplied by small f of xy minus big F of xy, right? So now we have this, of which is what? 2xy. So we're going to substitute that here. Then we're going to have our mu of x and y to be what? 1 over xy multiplied by what? 2xy. Okay, so we do that simplification, then we have our mu of xy to be equal to 1 over 2x squared y squared. Okay, so this becomes our what? Integrating factor. So we are going to use this integrating factor multiplied through by this function, this differential equation, and to make it exact, because as it stands, this is not exact. So we're going to multiply through by this integrating factor to make it what? Exact. Okay, so don't forget, this is our integrating factor. Okay, so we are going to multiply this by this. So we're going to have mu of x and y multiplied by this whole equation. So we have s squared y squared plus xy plus 1 dx plus s squared y squared minus xy plus 1 x dy equals 0, right? So we are going to multiply each item, right, by the integrating factor. So you're going to have 1 over 2x squared y squared, right? So we have x squared y squared plus xy plus 1 divided by, okay, multiplied by what? Y dx plus x squared y squared minus xy plus 1 x dy equals 0, right? Okay, so let's try to expand that. We are going to spread this throughout the whole bracket, right? So we're going to have x squared y squared plus xy plus 1 or y divided by 2x squared y squared dx, right? Plus x squared y squared minus xy plus 1 or x dy divided by 2x squared y squared, and that is equal to what? 0, because 0 multiplied by this will give us what? 0. So this is what we have. So let's try to simplify that. So we're going to simplify this, okay? But before then, let's try to spread this y throughout the bracket and spread this x throughout this bracket. So we're going to have x squared y, we're going to be y cubed, right? Plus xy squared plus y divided by 2x squared y squared, right? Or the x, right? Plus, we spread this x throughout the bracket. So we're going to have s cubed y squared minus x squared y plus x divided by 2x squared y squared or dy, and that is equal to 0. Okay, so we are heading towards uh, the end line to start the differentiation of the differential process, right? So you know that this can divide each of the item at the numerator, right? So we're going to have x squared y cubed divided by 2x squared y squared plus xy squared divided by 2s squared y squared plus y divided by 2s squared y squared, right? Or the x, right? Plus this 2 we spread. We divide each of the item at the numerator with the denominator, right? So we have s cubed y squared divided by 2s squared y squared minus s squared y divided by 2s squared y squared plus x divided by 2s squared y squared or dy, and that is equal to what? 0. So let's try to simplify h, right? So this will take 2 of this, we have y here, and this will take this. So we have y divided by 2, y divided by 2, right? So we have that plus this will take off this, left with 1, then this will take 1 of this. So we have y divided by 2x, right? So that is what we have there. Then plus this will take 1 of this. Then we have 1 over 2x squared y, or the x, plus this will take off this, it will take 2. Then we have this also take this, so we have x over 2, plus this will take off, this will take 1 of this, so we have y, and this will take off this, so we have 1 over 2y, right? Plus this will take 1 of this, so we have 1 over 2xy squared, or dy equals 0, right? So that is what we have at this moment. Okay, so this is our simplified differential equation. So this is what we are going to solve. Okay, this is, so now that we have this, the simplified equation, we can say that our m of x and y is equal to the function that is attached to the dx becomes your what, m of x and y. So we have y over 2 plus 1 over 2x plus 1 over 2s squared y, right? Then our n of x and y will be equal to x over 2 minus 1 over 2y plus 1 over 2xy squared, right? So that is our n of x and y. Okay, so this is what we have right now. But don't forget, we multiply through with what? An integrating factor. And once you multiply through with an integrating factor, automatically the differential equation becomes what? Exact. So this here, this and this, when we differentiate this with respect to y and differentiate this with respect to x, and the result must be equal. The results must be equal because that is the main goal. That is why we multiply through by the integrating factor. So here we're going to, let's say that this is equation 1 and this is what? Equation 2, right? So we're going to divide, we're going to differentiate m of x and y partially with respect to y, right? So when we do that, we are going to differentiate this partially with respect to y. So that means that this is going to be what? Half. Then this will go to 0 because it does not have any y term. Then we come here, we differentiate partially with respect to y. So it means that we're going to have minus 1 over 2x squared y squared, right? You know that this is the same as half times x to the negative 2 y to the negative 1. So when you are differentiating with respect to y, that means that we are going to subtract 1 from the y. It's going to be what? Minus 2. So when you bring it down, it's going to be what? S squared. So that is our differentiation. Now let's also differentiate this partially with respect to what? X, right? So partially with respect to x, we're going to have half minus, when you differentiate x over 2, you go out with respect to x, you have what? Half. Then this one goes what? 0. Then we come here, when you differentiate 1 over 2x y squared, you're going to have minus 1 over 2x squared y squared, right? So that is what we have. So we can see clearly that our two differentiation are equal. So that is differential of m of x and y with respect to y is equal to differential of what? N of x and y with respect to what? X. And that is equal to half minus 1 over 2x squared y squared. Right? So this shows that the differential equation is indeed an exact differential equation. So our exactness condition has satisfied. So that means that we can go ahead and solve the problem. So this confirms the exactness condition. Right. So this confirms the exactness condition. Okay, so once this has confirmed the exactness condition, then it means that there exists some function, some potential function, of which when you take the first derivative with respect to x, right, equals the m of x and y, and also you take the first derivative with respect to y equals the n of x and y, then that is what I mean. Since this is exact, then it means that there exists some potential function, right? That is f of x and y equals what? C. So this is the potential function that it exists, right? And we have a process that we will use to solve that. So we are going to go through the process to solve this equation to have our potential function, right? So that means that there exist two functions, right? So fs of x and y is equal to this, the first function, which is y over 2 plus 1 on 2x plus 1 on 2x squared y. And then fy of x and y equals the n of x and y. So we have x on 2 minus 1 on 2y plus 1 on 2x y squared, right? And that is, so we call this equation 3 and call this equation 4, right? Now, once you get here, the ball is in your court. It's either you use equation 3 to solve, then you come and do substitution, or you use equation 4 to solve, then you come and do substitution. So in here, I'm glad to use equation 3. You can also use equation 4. You arrive at the same process. So let's start. I'm going to use equation 3, right? So using equation 3, I'm going to consider the equation 3. So if whichever equation you consider, then if you consider the equation 3, you see this one is differentiated. So if you choose equation 3, then it means that you are going to integrate with respect to x. If you choose equation 4, then it means you are going to integrate with respect to x as your first method, right? So that we can get the potential function, right? So for me, I'm going to consider equation 3, right? You can as well consider equation 4. You also land on the same um, uh, land, right? So we're going to have, okay, let's write methods, right? So our first step is to integrate equation 3 with respect to x, right? So we're going to integrate fs of x and y with respect to x equals what? Integral of y on 2 plus 1 on 2x plus 1 on 2x squared y with respect to x, right? So when we do that, it means that this will cancel this. So we have f of x and y equals, when you integrate y on 2 with respect to x, we're going to have xy divided by 2 plus, when you integrate half x, you're going to have half ln x, right? We are integrating with respect to x. You know that 1 over x, when you integrate it, you have what? Ln x, right? So we have half ln x plus, when you integrate 1 over 2 x squared y, you're going to have minus 1 over 2x y. Okay, so this, at this point, whenever you do integration, you add a constant of integration, right? But here we are not going to add just a constant. We are going to use a constant of integration that involves y, because we integrated with respect to what? X. So our constant is going to what? Involve y. So plus a constant of what? Integration, which is j of y. So I use j of y. You can also as well use phi of y, anything that is nice, right? So let's call that equation 5, right? So we have this equation 5. Step 2, differentiate equation 5 with respect to y. So differentiate equation 5 with respect to y. So we are going to do that. We are going to have fy of x and y to be equal to, when you differentiate this with respect to y, then it means that we are going to have x on 2 with respect to y. So it means that this will go to 0, right? So we're going to have, this goes to 0. Then we are going to have differentiate with respect to y, right? So this goes to 0. Then we have this, right? So we're going to have plus 1 on 2x y squared plus 1 on 2xy squared plus our j prime of what? Y. Don't forget, after integration, we added a constant of what? J of y. So when you integrate, when you differentiate, then it will be what? J prime of what? Y. So we call that equation 6, right? So we can see that this equation 6 here, we have fy of x and y equals this. And then in equation 4, we also said fy of x and y equals that. So it means that equation 4 and equation 6 are the same. So equates, so that is step 3. Equates equation 4 and equation 6, right? So since fy of x and y equals this and fy of x and y equals that, then we are going to equate them. So we have xy, x on 2 minus y, 1 on 2y plus 1 on 2xy squared equals this, right? So we're going to have x on 2 plus 1 on 2xy squared plus j prime of what? Y. Okay, so this is what we have now. Okay, so we can do some simplification, right? So we can see clearly that if this comes here, this goes to 0. This comes here, this also goes to 0. So we're going to have only this and the j prime of what? Y. So we have negative 1 over 2y equals j prime of what? Y. So we have, this implies that j prime of y is equal to negative 1 over 2y. You know that when you are integrating this, then it means that this will take off this, then this will also take off, this will take off that. Okay, this will take off that. So we have j of y equals negative 1 on 2 ln y plus a constant of integration, right? So integral of negative 1 on 2y is what? Negative ln y plus what? A constant of integration, say c1. Okay, so now that we have j of y equals what? Negative half ln y plus c1, then means that we can substitute that into what? Equation 5, of which we have equation 5 in terms of what? J of y. So we're going to substitute j of y into equation 5. So let's call that equation 8. So put, that is step 5, put 8 into what? 5, right? So we are going to have, f of x and y equals xy over 2 plus 1 on 2 ln x minus 1 on 2 xy plus j of y is now negative half ln y. So we have minus negative half ln y, right? Plus a constant, say c1, right? So don't forget that this is the potential function, and that is what? C. So but f of x and y is equal to c. So let c equals what? C1. So we call that C1 minus what? C. Okay, this is C, right? So we are saying that C should be equal to what? C1 minus what? C. So they are all constant. So we are interested in only one. So we say that this whole function is equal to C. C equals what? Xy divided by 2 plus half ln x minus 1 on 2 xy minus half ln y minus half ln y. Okay, because we already said that c minus c1 should be what? C. So let me come up here and write the final answer for you. So we're going to say that we have xy on 2 plus half ln x minus 1 on 2 xy minus half ln y, and that is equal to what? C. Okay, so this is what we have as our final solution. But don't forget, we have 2 running through each of the items, so we can multiply each of the item by what? 2, so that this fraction, this 2 2 2 2 goes away. So we're going to have x y divided by 2 times 2 plus 2 times 1 on 2 ln x minus half xy times 2 minus half ln y times what 2. So this takes of this, and this takes of this, and this takes of this, and this also takes of that. That is equal to what? C. So we say that our xy plus ln x minus 1 over xy minus ln y, and that is equal to a constant. So this is our potential function, which represents what? The general solution. The general solution. So this becomes our final answer to the differential equation. This becomes our final answer to the differential equation. Xy plus ln into x minus 1 over xy minus ln into y equals what? C. And that is the solution to question number 1. In our previous video, we had the same solution. We have a solution that we are supposed to simplify to come and have this, but we didn't simplify. So don't be worried. The solution we had in the previous video and this, they are all the same, where we used the substitution and we had xy plus ln x minus 1 on xy equals 2 ln y, right? Equals 2 ln y plus c. This is what we have in our previous video, right? This and this are all the same. When you simplify this, you come and have this. So don't be worried about that. I forgot to simplify. Pardon me for that. So this becomes our clear solution. This is more clearer, right? So this is our final solution to the question number 1. Okay, so let's move on to question number 2. We are going to take it step by step to make everything crystal clear. All right, so let's dive. Okay, so with question number 2, we want to prove that this x to the y, x to the h, and y to the k is an integrating factor of py dx plus qx dy plus x to the y, x to the m times y to the n, all multiplied by y r or ry dx plus xx dy, or brackets close, equals 0. If it's on the condition, right? This question is on a condition, right? So if h plus 1 over p is equal to k plus 1 over q, and h plus m plus 1 over r is equal to k plus n plus 1 over what? X. Okay, so after that, we want to use that method to solve this differential equation. Okay, so this is as well, it's going to form an exact differential equation, then we solve it. But as it stands now, this is not exact. So we are going to look for that exact integrating factor that we are going to multiply to have what? Exact, right? So that is why we'll be doing all this before we come and do this. Other than that, this is the main work, right? So in here, this is not exact, and we have to make it what? Exact. Okay, so let's start the process. So this is question number 2. Of course, during your assignment, I was so exhausted, so I couldn't give you the solution. But I know you had the right answer to for the submission. So now let's dive into it. We are going to take it step by step, right? So that you get it clear. So that whenever you meet it anywhere in your exams or whatever it is, you'll be able to handle it so nicely. All right, so our first step that we are going to do is to what? Expand this equation. Expand and group like terms. So our first step, step one, expand and group like terms, right? Expand and group like terms of this particular equation, right? So we are going to do that. So we have py dx plus qx dy plus r, where we are expanding this, right? So we have r x to the m y to the n plus 1. It's multiplying, so we add the exponent. So we have y to the n plus 1 or the x plus the same item multiplies this section out. So we have x to the m plus what? 1. So let me bring the r first so that it doesn't look something else. So we have x to the m plus 1. Then we have our y. So rsy x to the m plus 1. rsy rx, you know, if you try to be smart, you have to be very smart enough. So we have r, then y is having what? To the power n, and this is what? Power 1. So you're going to go what? N plus 1. Then x is to the power m here, and we have 1x here. So we're going to go what? X to the power m plus 1. Then we have x, right? So we have rx. Okay, so all this dy, right? All this dy. Okay, so now that we have this, let's try to group like terms. So we can see that we have the x here and we have the x here. We have dy here, we have dy here. So we group like terms. So we're going to say that py dx plus this rx to the m y to the n plus 1 or dx plus qx dy plus rx y to the n plus 1 x to the m plus 1 or dy, right? So we're going to combine that. So we're going to have this here. So we say that, this is the x and this is what? The y. Okay, this is the x and this is what? The y. So the next step that we have to follow is that step 2. Step 2, let's try to assume, now that we have expand and simplify and group like terms of this particular equation, then the next step is, we are proving that x to the h, y to the k is an integrating factor to this particular equation that we just simplify and group like terms, right? So let's try to, this, we don't know the exact value for h and k. That is why they've given us conditions. So we are going to do that. Okay, so let's try to assume an integrating factor of this nature, right? So let's assume an integrating factor of the form mu of x and y equals x to the h, y to the k, right? So we assume an integrating factor of the form x to the h, y to the what? K. So then we have to say that the new differential equation, right? The new differential equation here becomes the new then the new differential equation becomes m mu of x and y multiplied by m of x and y or the x plus mu of x and y multiplied by n of x and y dy is equal to what? 0, right? So that is how our new differential equation will look like. We multiply each of what? The term, the dx by m of x and y, and then the dy by what? Mu of x and y. So what we are going to do is that, don't forget that our m of x and y is this, right? So don't forget that our m of x and y is equal to py plus py plus r x to the m y to the n plus 1, or the x and then our n of x and y is equal to the term containing the what? The dy. So we have qx plus rsy n to the what? Y to the n plus 1, then x to the what? M plus 1. Okay, so that is our n of x and y. So always, this is how you identify your m of x and y and your what? N of x and y. Your m of x and y is the term that is attached to what? The dx. And your n of x and y is the term that is attached to what? The dy. Okay, so now that we know how to identify our m of x and y and our n of x and y as we have them here, then let's try to form the new differential equation. Okay, so it means that we are going to multiply this by the new by our what? Mu of x and y. So we're going to have that the first part to be what? Mu of x and y times m of x and y to be equal to this times this, right? So we have x to the h, y to the k multiplied by py plus rx to the m, y to the n plus 1. Yeah, y to the n plus 1. Then our mu of x and y times n of x and y will be equal to x to the h, y to the k multiplied by this, right? So we have qx plus rx, y to the n plus 1, x to the m plus 1, right? So let's try to expand each of the term, right? I'm going to expand each of the term. Then we know our mu of x and y times what? M of x and y. So now our mu of x and y times m of x and y will be equal to, we are going to expand this right here. Okay, so we're going to have px to the h, y to the k plus 1 plus x to the h, x to the h plus m, x to the h plus m, x to the h plus m, yeah, okay. Then we have y to the k plus n plus 1. Then we have our rs, yeah, our r. Okay, so this is for the mu of x and y times m of x and y. Then we have our mu of x and y times n of x and y, and that will be equal to this times this becomes x to the h plus 1, y to the k q plus rs, y to the k plus n plus 1, x to the m plus h plus 1. Okay, so this is what we have for the mu of x and y times n of x and y. Okay, so once we have that, then our next step is to check the exactness, right? So for exactness, for exactness to hold, then it means that differential of mu of x and y times m of x and y with respect to y should be equal to differential of m of x and y times n of x and y with respect to what? Y. So differential of m of x and y times m of x and y with respect to y should be equal to differential of n of x, differential of mu of x and y times n of x and y with respect to x. So for the exactness to hold, this is what should happen. Okay, this is what should happen. So step 4, what are we going to do? Step that is, this is step 3, right? So that is going to be this is step 2, so that is going to be step 3. So step 3, we are going to differentiate this with respect to y, then we differentiate this with respect to x and see if the result will give us the same. Okay, so we are going to do that. So here we are going to differentiate this. So let's say that this is equation 1 and this is equation 2. So we differentiate that. So we are going to differentiate mu of x and y with respect to mu of x and y times m of x and y with respect to y here with respect to y, okay, then it means that the exponent of y here will come down. So we have k plus 1 multiplied by k plus 1, then it will reduce by 1, right? So we have y to the k times x to the h times x to the hp, right? Plus we are we are differentiating with respect to y. So it means that the exponent here will drop. So we have k plus n plus 1, right? Then this will reduce by 1. So it means that this one will go off. So we're going to have y to the k plus n. Then we have x to the h plus m, right? Then this is what? This is r, right? So this is what we have. Now let's go and differentiate this as well with respect to x and see what we're going to have. So we differentiate that. Differentiate mu of x and y times n of x and y with respect to x and see what we're going to have. So we differentiate this with respect to x. We're going to have h plus 1, then x to the h, y to the k, q, plus we differentiate here as well with respect to x. So it means that the exponent here will drop. So we have m plus h plus 1, right? Then we have x to the m plus what? H times what? Rx y to the k plus n plus 1, right? Okay, so that is what we have. So for this to hold, that means that the coefficient of x to the h, y to the k must be equal, right? The coefficient of x to the h, y to the k must be equal. So let's look at it. We have k plus 1, and then we have k plus 1 p, and we have k h plus 1 q. So for this to hold, that means that the coefficient of x to the h, y to the k, then the same thing here must be equal. So we're going to have h plus 1 or q should be equal to what? K plus 1 or p. For the condition to hold, we have to also check this part. So you're going to have k plus n plus 1 or r should be equal to m plus h plus 1 or s, right? So that is what we have here. So we're going to say that so we're going to say that in all, what we are trying to say is that k plus 1 over k plus 1 over q should be equal to h plus 1 over what? P. What you are trying to say is that if you divide k plus 1 by q and you divide h plus 1 by p, then they all should be what? Equal, as the question gave us, that if that condition, then the same thing applies here. K plus 1, k plus n plus 1 divided by x should be equal to m plus h plus 1 divided by what? R. So we have that to be there. So for that proof to work, then means that this and this should be equal, and this two should be equal, right? So we need to continue from there. We need to continue from there. So this means that this means that this means that this proves or this proves that if these things work, or if these conditions hold, then mu of x and y equals is x to the h, y to the k is indeed an integrating factor. Okay, so if these conditions hold, then it means that mu of x and y, which is equal to the integrating factor they gave to us, s to the h, y to the k, is indeed an integrating factor if only these conditions hold, right? So we are going to use this method to solve the differential equation. So using this method to solve 3y minus 3y dx minus 2x dy plus x squared y minus x squared y to the negative 1 into 10y dx minus 6x dy, and that is equal to 0. So now we are going to use this method to solve this differential equation. So you can see that this question, how it has been framed, is different from the previous question, the question number 1. So in here, we are supposed to use the integrating factor to solve this differential equation. If you don't use the integrating factor approach, you are wrong. But previous question, we were not asked to use the integrating factor compulsory, right? So in that instance, we were able to use the substitution for our previous video, and in here we use the integrating factor. Okay, so we are going to continue from there. So let's expand and simplify this equation. So expand and simplify this equation, right? So what I mean is that you see we have x squared y to the negative 1 multiplied by this. So we're going to expand that, then we simplify the equation. So we're going to have 3y dx minus 2x dy plus 10x squared y to the 0, right? So we have negative 1 plus 1, right? So we're going to be what? Y to the 0, of which is 1. So we're going to have the x minus 6x cubed y to the negative 1 dy. and that is equal to 0. That is equal to 0. So this is what we have. Let's try to simplify that. So this is the x, and this is also the x. So we're going to have 3y plus 10x squared dx plus negative 2x minus 6x cubed y to the negative 1, or dy equals 0. So this is what we have upon our expansion and simplification. So let's go up here. So we go up there, then we say that we have already grouped like terms, right? So we group like terms, we group all with the x to one side, and we group all with the y to one side. Okay, so the next thing to do is to, compare this equation to the previous equation that we expand and simplify, of which it's py dx plus qx dy plus x to the m y to the n into ry dx plus xx dy equals 0. Right. So we are going to compare this equation to this particular equation. All right. So what are we going to do? We can see that we have py here and we have 3y here. So it means that this implies that py is equal to what? 3y. So we are comparing this equation to this particular equation, right? So we have py equals what? 3y, right? From here. So we're going to have, this implies that our p is equal to what? 3. Okay, so we have obtained the value of what? P, right? Now, we can also, okay, so now that we have this, so now we are going to compare this equation with this, right? So let's try to expand this and expand this so that we can compare the coefficients, right? So let's do this first. We're going to have py dx plus qx dy plus, we expand this, we are going to have x to the m y to the n plus 1. Here we have y to the n here, and we have y here. So this is exponent 1. So add up to this, we have n plus 1. Then we have our r in front, right? Then we have the x plus this times this. We are going to have x to the m plus 1 y to the n dy equals 0. Right? So this comes here. We have x to the m plus 1, and that is there. And then we have y to the n. Then we have our x, which we have here. Then we have dy, all equals 0. So we have this. Now let's expand this as well. We're going to have 3y dx plus 10x squared dx minus 2x dy minus 6x cubed y to the negative 1 dy, and that is equal to 0. So we are comparing this with this, right? So this to this, you can see that the coefficient of the x here is what? Py, and this is what? 3y. So it means that we have 3y equals py. So it means that this implies that our p is equal to 3, right? And also qx to dy here is what? The coefficient of dy here is what? Negative 2x, and the coefficient of dy here is what? Qx. So we're going to say that our qx is equal to what? Negative 2x. So this implies that our q is what? Negative 2, right? Then we compare this as well. The coefficient of the x here is what? R x to the m y to the n plus 1. So we have r x to the m y to the n plus 1 equals the coefficient of the x here too is what? 10x squared, right? So we know the coefficient of the x here to be 10x squared and the coefficient of the x here to be this. So we compare that, and this is what we have. So this basically tells us that the exponent, right? When we compare the exponent, right, then it means that the exponent of x here is what? M, and the exponent of x here is what? 2. So this means that our m is equal to what? 2, right? So we have the value of m as well. And we can see that the exponent of y here is what? N plus 1, right? And we don't have any exponent of y here. So let's relax for this. Then we go for this for now. So we're going to say that, okay, so as well, we can see that the coefficient of x to the m, which is the coefficient of x squared, is what? R, and that here is 10. So we have our R to be equal to 10, right? Now we have R, we have m. So let's come here. The coefficient of dy here is what? X, the x to the what? M plus 1, y to the n equals, the coefficient of dy here is negative 6, x to the 3, y to the negative 1, right? So we can see that when we compare this, the coefficient of x here is what? The coefficient of cross x here is what? S, and that is equal to what? The coefficient of s here is what? Negative 6. So we have the value of what? X. And when we compare this to this, right, we're going to say that we have what? M plus 1 equals what? 3, right? The exponent to this, m plus 1 equals 3. So this implies that our m is equal to what? 2, as we already had here. So we have the value of what? M. Now, let's look at the exponent of what? Y. Exponent of y here is what? Negative 1, and the exponent of y here is what? N. So we have n equals negative 1. So we have also the value of what? N to be what? Negative 1. So we can see that we've obtained all the values that we need, right? Yeah, we have all the values that we need. So once we have the values that we need, we're going to substitute into this so that we can solve for k and h and check if this is equal to this and this is equal to this. Then we can proceed and solve this differential equation, right? So let's substitute the values of m, s, r, p, and q into this expression. So we're going to say that k plus 1 divided by q is minus 2 equals h plus 1 divided by p is 3, right? So let's note this down. And then we have k plus n is what? -1. So we have -1 plus 1 divided by s. S is -6 equals m. Our m is what? 2. So we have 2 plus h plus 1 divided by r. R is 10. So we have 10 here, right? So when we simplify this, we are going to have this takes of this. We have k over -6 equals 3 plus h divided by 10. So we have this. Okay, so let's try to transform this into equation and then transform this as well into equation so that we have two systems of equation with two unknowns so that we solve the h and the k. Okay, so we're going to do that. So we say that this k plus 1 divided by -2 equals h plus 1 divided by 3, right? So we cross multiply and we're going to have 3 into k plus 1 equals -2 into h plus 1, right? So you have 3k plus 3 equals -2h minus 2, right? So we simplify this, and we have 3k plus 2h equals what? 5 equals -5, right? Because -2 then -3 becomes -5. So we have equation 1. Then we consider this as well. K over -6 equals 3 plus h over 10, right? So cross multiply. Now that we have equation 1, we consider this as well. So we have k over -6 equals 3 plus h over 10. So let's expand that. So we got 10k equals -6 times 3 becomes -18 minus 6h, right? So we group terms. So we have 10k plus 6h equals -18, and that is equation 2, right? Now we want to solve this equation 1 and 2 simultaneously. So what do? We can either use substitution or elimination. So by elimination, I'm interested in elimination. It's so fast. So by elimination, we multiply equation. We want to eliminate h, right? So we multiply equation 1 by 3 so that we have 6 here, and then we can have equal coefficients here. So we multiply equation 1 by 3, right? So we're going to have 9k plus 6h equals -15. So we have equation 3. So now that we have equation 3 and we have equation 2, let's try to subtract equation 3 from equation 2. So 3 from 2, right? So we're going to have 10k plus 6h equals -18 minus 9k plus 6h equals -15, right? So this minus this becomes k. This minus this becomes 0. Then -18 minus -15 becomes -18 minus -15 becomes -3, right? So we have -3 for our k, right? So once we have our k to be -3, we can substitute into either equation 3 or equation 2 to find our h, right? So let's call that equation 4, right? So we're going to clean this. So put 3 into what? Put 4 into 3, right? So we're going to put equation 4 into 3 to have h. So we have 9 into our k is minus 3 plus 6h equals negative 15. So we have negative 27 plus 6h equals negative 15. So we have 6h equals negative 15 plus 27. So 6, we have our 6h to be equal to minus 15 plus 27 is basically minus 12, right? 27 minus 12. 27 minus 15 is 12, right? So we have 12 here. So we divide here by 6, here by 6. This implies that our h is what? 2. Okay, so we have the value of what? H to be 2, the value of k to be minus 3. So what are we going to do? We are going to put it into the from the beginning. Realize that they said we should prove that s to the h, y to the k is an integrating factor. Okay, so if you know that, then let's do that. So let's put h value here. We had 2. Okay, so I'm going to erase this. I'm going to erase this, right? So now our integrating factor mu of x and y will be equal to x to the h, y to the k, where our h is equal to 2, our k is equal to what? Minus 3. So we're going to substitute that so that we have our actual integrating factor to be what? X to the what? 2, y to the negative 3. Okay, so this is our integrating factor, right? So we've obtained our integrating factor. So what do we do next? Once we have the integrating factor, then it means that we are going to multiply the integrating factor by the differential equation so that it becomes exact, right? So we're going to do that so that it becomes exact, and then we can solve it. Okay, so what we do, this is our differential equation, and we want to multiply it by the integrating factor so that it becomes exact. Okay, so we're going to multiply the differential equation by the integrating factor. Mu of x and y equals what? X squared y to the negative 3, right? This is our integrating factor. So we have proof for that. So let's try to multiply through by that. So when we do that, we have mu of x and y multiplied by, this is the differential equation, right? So we're going to have 3y plus 10x squared, or the x plus negative 2x minus 6s cubed y to the negative 1 dy, right, equals 0, or multiplied by the mu of x and y. So we know that our mu of x and y is x squared y to the negative 3. So we have x squared y to the negative 3 into 3y plus 10x squared, or the x plus negative 2x negative 6x cubed y to negative 1 dy equals 0. Okay, so we're going to expand that. I'm going to expand that So we expand that, we're going to have this times this, we're going to have 3x squared y to the negative 3y plus 10x squared y to the negative 3, or the x, plus negative 2x times x squared y to the negative 3 minus 6x cubed y to the negative 1 x squared y to the negative 3, or dy equals 0. Okay, so we are going to do that simplification. Then we're going to have 3x, this becomes squared, then minus 3 plus 1 becomes y to the negative 2 plus 10x squared y to the negative 3, or the x, plus x, then x squared becomes x cubed y to the negative 3 minus 6x to the 5 y to the negative 4, or dy equals 0. Okay, so this is the simplified differential equation that we have. So this becomes our new differential equation. So this becomes our new differential equation, right? So this becomes our new differential equation. Okay, so this, we are going to use the exact method to solve it, because we can see that this has been quantified in the nature of uh, how we approach the exact differential equation, right? So we know that the term that is attached to the dx is our m of x and y, right? So the term that is attached to the dx is our m of x and y, right? So we say that our m of x and y is equal to 3x squared y to the negative 2 plus 10x squared y to the negative 3. And our n of x and y is equal to negative 2x cubed y to the negative 3 minus 6x5 y to the negative 4. Right, so this is our m of x and y and our n of x and y. Okay, so yeah. Okay, okay, so we have that here. Okay, see, it's to the 4, right? It's to the 4, you know, when you this where is it? From here, from here, x to this s squared, then s squared becomes s to the 4. So we have x to the 4 here. So this part is supposed to be what? X to the 4, y to the negative 3. So exactly. Okay, so this is correct. So the next thing we have to do is, let's consider this to be equation 1 and this to be equation 2. So now that we have our m of x and y and we have our n of x and y correctly, then we are going, let's still check for exactness. Even though when you multiply the differential equation by the integrating factor, it tends to exact automatically. But for some reason, let's try to check for exactness and see that, and check if these things are the same, right? So we're going to check that. So we're going to check that. So for exactness, we know that we're going to differentiate our m of x and y with respect to y, right? So this here, we differentiate with respect to y. So when you do that, we're going to have negative 6 x squared y to the negative 3, right? Then with respect to y, we're going to have minus 30 x to the 4 y to the negative 4, right? Then we differentiate n of x and y with respect to x, and that will also give us, with respect to x, that will give us minus 6x squared y to the negative 3 minus 30x to the 4 y to the negative 4, right? So we can see that this and this are equal, right? Okay, so that means that the die of x, die m of x and y with respect to y is equal to die n of x and y with respect to what? X, and that is equal to negative 6 x squared y to the negative 3 minus 30 x to the 4 y to the negative what? 4, right? So this condition holds. Okay, so once this condition holds, then it means that there exists a potential function f of x and y equals what? C. And how do we get that? We're going to go through the process. So from here, since this and this are the same, then it means that there exists a potential function of which is f of x and y equals what? C. How do we get that? So this is how we get that. So these are the functions that exist. So we differentiate the function with respect to x of what? X and y equals what? The m of x and y. And that is equal to, we had 3x squared y to the negative 2 plus 10x to the 4 y to the negative 3, right? Then there is another function. So we consider this to be what? Equation 3, and this to be equation 4. Don't forget that our m of x and y, I'll state that as well. So this is also equal to n of x and y. Okay, and that is equal to minus 2x cubed y to the negative 3 minus 6x to the 5 y to the negative 4, and that is equation equation 4, right? So we have equation 3, equation 4. So I want to state this here before we continue. So I want to put this down. Our m of x and y is equal to 3x squared y to the negative 2 plus 10 x to the 4, y to the negative 3. And this is equation 1. N of x and y equals what? Negative 2x cubed y to the negative 3 minus 6x to the 5 y to the negative 4. And this is what? Equation 2. So now that we have our potential function, of which is f of x and y equals what? C, we know that there exists a potential function f of x and y equals c. Then it means that we have to solve these two equations. Now, the ball lies in your court. It's either you choose equation 3, then you solve, come and substitute into equation 4, or you pick equation 4, solve, and come and substitute into equation 3. Now, listen to this. If you solve equation, if you are holding equation 3, then it means that you are going to integrate with respect to x. That is the first step to be able to get the what? The potential function. So, first step, so methods. 1. Step 1. Integrate equation 3 with respect to x, right? So we're going to integrate this with respect to x. So we're going to have fs, integral of fs of x and y equals what? 3x squared y to the negative 2 plus 10x to the 4 y to the negative 3. We are integrating this with respect to x, right? So this will cancel this. So we have f of x and y is equal to, we are integrating with respect to x. So we are going to have 3x cubed y to the negative 2 divided by 3, right? We know that we add 1 to the exponent of x, then becomes 3. We use the 3 to the... Okay, so from here, we have what? With respect to x, right? So we're going to have, we are integrating. So we're going to have 10x to the 5, y to the negative 3, divided by 5, right? Plus our constant of integration. But at this point, it's not going to be what? Constant of integration, which is going to be c, but this is going to be j of y, because it's of two variables and we integrated with respect to what? X. So it means that the constant is going to be in terms of what? Y. So our constant is going to be what? J of what? Y. Okay, so let's simplify that. We're going to have f of x and y to be equal to, this cancels this. We have s cubed y to the negative 2 plus, this is going to be plus 2x plus 2x to the 5 y to the negative 3 plus y, j of what? Y. Okay, so let's call this equation 5. Okay, so we are calling that equation 5. So once we have this, then the next thing is to differentiate equation 5 with respect to y, right? So that is step 2. So we are going to differentiate this with respect to what? Y. So differentiate with respect to y, differentiate partially with respect to y of f of x and y, and that will be equal to differential of x with respect to y of what? S cubed y to the negative 2 plus 2x to the 5 y to the negative 3 plus g of y, right? Okay, so this is what we have. We are going to differentiate partially with respect to what? Y. So that means that we're going to have fy of x and y equals with respect to y. So we're going to have x cubed y to the negative 3, right? In differentiating with respect to what? With respect to y. So so we're going to have minus 2 here, right? So minus 2x to the 3, y to the what? Minus 3, right? Then plus, with respect to y, we're going to have minus 6 x to the 5, y to the negative 4, plus j prime of what? Y. So let's consider this to be what? Equation 6. Now, from equation 6 and equation 4, we can see that they are the same, right? We have fy of x and y equals that, and we have fy of x and y equals that. So it means this and this are the same, so we can equate the right hand side. So equate 4 and 5, 4 and 6, right? So we're going to have negative 2x keep y to the negative 3 minus 6x to the 5 y to the negative 4 equals this minus 2x to the 3 y to the negative 3 minus 6x to the 5 y to the negative 4 plus j prime of what? Y, right? So now let's try to simplify that. So we simplify that. We can see that if this comes here, this will go off, right? And then if this comes here, this will also go off. So we're going to have 0 equals j prime of what? Y, right? So that is what we have from equation, from this simplification. If this, when you send everything here, they will cancel out and go to 0. So we have 0 equals j prime of y. So this next step, which is step what? Step 3, integrate. So we consider this to what? Equation 8. Integrate 8 with respect to y. So we integrate 0 with respect to y, integrate j prime of y with respect to y, right? So this cancels this. We're going to have a constant, right? When integrate 0 with respect to y, you're going to have a constant. So let's say that constant is what? C1. The reason why we are calling it C1 here, not G prime, G of Y, is that we are dealing with only one variable. We are integrating with respect to only one variable. But from here, where we introduce G of Y, we were integrating with respect to two variables, right? It was with respect to two variables, and we were integrating with respect to what? X. So we have to let our constant be what? The one that we are not touching. But in here, we are integrating with respect to what? Only y. And the whole term is with respect to only y. So we have our constant c, our normal kind of integration, right? So that is equal to this cancels this, right? So we have our j of y to be equal to that. Okay, so you can say that j of y is equal to C1, right? So let's call that equation 9. Okay, so now that we have G of y equals C1, then it means that we can substitute G of y equals C1 into what? Equation 5, because we have, in equation 5, we have G of y. So in a nutshell, we can say that we are bringing the work to an end. So we can say that put 9 into what? Equation 5. So we're going to have f of x and y to be equal to x cubed y to the negative 2 plus 2x to the 5, y to the negative 3, plus our g of y is c1. So we have c1, right? So this is our potential function. But don't forget that we said f of x and y should be equal to what? C. Okay, so we're going to say that c equals x cubed y to the negative 2 plus 2x to the 5 y to the negative 3 plus c1. But this and this, they are all constant, right? So we can say that c should be equal to c minus what? C1, right? So we're going to represent c with what? This and this, right? So we have what? Our c should be equal to what? S cubed y to the negative 2 plus 2x to the 5 y to the what? Negative 3. So we simplify that. And we're going to have x to the 3 y to the negative 2 plus 2x to the 5 y to the negative 3, and that is equal to what? C. Okay, this becomes what? Our general solution. This is our potential function. This is our potential function. Or more clearly, we can say that we have x to the 3, y, x to the 3 over y squared plus 2x to the 5 over y cubed, right? And that is equal to what? C. Great. So this is the general solution. This is the general solution which represents our potential function. If we were to be given initials, then we will find a C, but we don't have any initial here. So that is the end of the problem. All right. So thank you very much for watching. I really appreciate your time. Please, don't forget to subscribe, share with your mates worldwide, and I'm going to give you more updates. Until the next video, please keep learning and stay inspired. Bye-bye.